Thank you very much, everyone, for coming. So today I'll be talking about Manage, in line with the first topic of this ADASS, managing workflows and reproducibility. In parallel, we have as you all know, the Discord channel that you can see here. I've already put some links. The slides are already on Discord channel. Please feel free to ask any questions during the talk. Of course, I'm talking now, but after the talk, I'll be very happy to answer them. Okay, so the basic idea behind, when we talk about pipelines, the most generic idea of a pipeline, what is it? It's just we have software, we have data, like our data comes from a telescope, we have some software, we build the software, we run the software on the data, and boom, we have our paper or data release, right? And this is a very high-level view of a workflow, right? But in the process, there's many questions that we can, if we just take these steps and ignore these questions or don't try to answer them properly, the validity of our final result really goes into question, because many things behind the scenes are very important. And this is a really important problem, both in the sciences and in the data analysis world, that we have, that it's very important to keep a lineage of the data and the software, and of course the data, the processing, and the final reduced data. And this is a very well-known problem in the community. There was this paper in 2016 which has become famous. It's Nature had asked like 1,500 people that are published in Nature before, that is there a reproducible crisis? And you see only 10% say no. 52% say yes, there is a significant crisis, and 38% say there is a crisis, but it's not too significant. This is from all the fields, it's not just astronomy. So since time is limited, I'll just jump directly to the method. And of course, there's a full paper on this, and this is the link here. It was published a few months ago in Computing in Science and Engineering, and it's also available on archives. The basic idea is that when we look at this plot here, the basic problem that most people fall into is that science is kind of driven, we feel that science is driven by its results. However, science is defined by its method, not its results. The method of obtaining the result defines the result and the validity of the result. It's not the result itself. So how do we teach this? Now, this is a very technical, philosophical, let's say, point, but let's get to a more concrete set of things. How do we define this method and that a scientist's result should be defined by? Okay, so we're talking about the computational science here. So, laboratory work or going to the observatory is not in the scope of this discussion, because they are before data comes into a computer. So the moment the file or data comes from a telescope or microscope or I don't know, whatever real world instrument we have, the moment it's stored as a file, we're talking from after that, not about like how to obtain data in a replicable way. Okay, so so these are the set of premises that we as time, while we were working on this, came up for us. And one of the first ones is that the project should be complete. So effectively, it should only rely on a minimal Unix-like system, which can be named POSIX, is commonly known as a minimal system. It shouldn't require root access. It should be able to run non-interactively, because human intervention means incompleteness, right? At the moment a human comes in, reproducibility comes out. Should be done without without internet connection. Should be used, so it should be doable without internet. So all the components of the analysis should be able to be kept on one computer, as far as like the volume and things allow. Okay, it should be modular. It should be in plain text, because now this is an important thing that I'll touch upon in a few slides later as well. But it's very important that the project be in plain text, because binary formats need special software, and those software are going to be depreciated. The plain text is not. ASCII or Unicode are not going to be depreciated in the foreseeable future. However, if you have a Docker file, Docker version XY, it's not going to support that version anymore in like 10 years. Or if you have, I don't know, some binary format anywhere. So that the project should be plain text. It will also allow version control. It should be minimally complex. The inputs and outputs should be automatically verifiable. And finally, of course, it should all be free and open source software. If it's not free, yeah, I would argue it's not reproducible. Okay, so let's get to our solution. So that was the principles that we've been working on that are the founding basis for this method. So let's get to the first set of questions about the software and how you build them. So as we said, this whole project, this whole method, Maneage, we call it managing data lineage. So we've merged the Maneage and lineage together to make Maneage. So in Maneage, everything is plain text. Everything is plain text. Nothing is from is any other format. And so over here in the next few slides, I'll just show in a tiny text editor that you can see some aspects of what I'm talking about. So in the part about software building and the necessary environment, in Maneage, initially we were thinking of just using like the operating system package managers or things like Conda, they have a big problem because they're third party to the project. So they're not the, if you want, so for example, this is like Conda on GNU Astro on Conda. You see the web page here. So look, for example, these are version 16, right? For version 16 of GNU Astro that just came a few weeks ago, there's already 2 versions on Conda because after we released version 16, Cifix.io, which is the dependency of GNU Astro, was updated. So if you just run Conda activate GNU Astro, you're going to get a different version of built GNU Astro. And it is possible within Conda to keep these dependencies and use this hash to identify it. But to be honest, I haven't seen it used too much in many papers that work on reproducibility. And also the operating system. So for example, many people go to Docker, but then or containers. But then, for example, in Docker, when you say from Ubuntu, for example, you want to in your Docker file, you want to start your operating system. So say you want a relatively older, let's say stable operating system, like say from Ubuntu 16.04 that came in April 2016. If you include this line in your Docker file, and only this line, it even includes the version of Ubuntu. Now click on this. This is where the ISO image comes from. Look, the dates are 2021. Just this month, right? It just came like 2 months ago, and these are the latest versions. So even when you just run when you give the version of the operating system, you're going to get a different base operating system every time. It's going to have different changes. It's changes, and it's really important to understand that these create those low-level things that change every time you create a new Docker image or run the Conda file. Unless you have everything under control, which is possible, but because it's third party to the research project and the pipeline and workflow, it's usually very hard. So in Maneage, we just decided to include the build instructions for all the necessary software of our project inside the project. So for example, this is the dependency tree of matplotlib. Just look at all the dependencies. So we have versions of, we have the instructions, for example, of matplotlib is inside Maneage. So you see it builds everything within the plain text, with plain text files that are managed with Make. So it builds the full software environment all the way from the high-level science software. So for example, over here, I've highlighted like Python, AstroPy, or GNU Astro. You can see like it has these versions. And from the high-level science software, it goes all the way down to even building the C compiler. That is the core of all the software in your project. So besides the C compiler, it also builds LS, CP, make the, everything. It even builds LaTeX, which we need for the paper. It doesn't need root permission, so you just give one directory, and it will take like usually 1.5 to 2 hours to build everything from source. And the thing is that even the tarballs necessary to build the software, we have our own separate repository for it that's just opening up right now. It's on Zenodo, which is managed by CERN. And so all of the tarballs that are necessary in a managed project are actually archived here. Then because we build the software and because we're scientists, because all the package managers are usually created by non-scientists, they're like software engineers, we actually include the citation of the software within the project. So because the ultimate goal of a science, let's say, pipeline workflow is to create a paper, is to create a report of a data release or something. So you see over here, we have in this paragraph is created automatically by Maneage as a LaTeX macro that includes the citations to all the necessary software. So as the author, you don't have to worry about not forgetting to cite. And then, okay, so now we're coming to the third branch, which is data. So for data, we include the full URL of every input data that's necessary and an MD5 checksum that will check the input data as it gets downloaded or if it's already available on the computer. Then for running the project, so Maneage is fully, let's say the workflow is managed in Make because we want long-term reproducibility, right? We don't want the fancy tool that came out yesterday and is going to be depreciated 2 days later. You know, we want that like in 40 years, we can open this and run it. And the only thing that is guaranteed to stay for 40 years is Make. Because the whole operating system that we use today is built with Make, and it's been here for 40 years, and it's going to stay until a revolution happens in computing that changes our operating system. And in Make, managing dependencies is very easy because in Make, you see, you have the full command as a simple plain text file, and you just define dependencies. And from those dependencies, a nice workflow is created, and only things that are necessary to be built are run. And finally, the report or paper. So for the report and paper, I'm showing this tiny paragraph from the noise chisel paper as part of the Nuastra that we had a tutorial a few days ago. So in this paper, have a look, these numbers in the PDF of the paper, in the LaTeX source, they're not numbers. They're LaTeX macros. And then these LaTeX macros come from this file that contains all of these macros, the numbers, and then these numbers are generated at the same processing phase that the process, you know, the analysis that we report in the paper or data release report was done. And you see, so we're able to, anytime something in the analysis changes, the paper will be automatically updated. So as an example, I will just reproduce this tiny plot from a paper that worked on counting how many papers cite software. And so just as a tiny workflow, I'll just show the whole structure of Maneage. So the whole, because it's in Make, it's good to see everything from the reverse, from the end to the start. So look, we have paper PDF is, you know, the final goal of any research project, right? So paper PDF, you see the green boxes are files that the user has written with their hand, and the blue boxes are files that are created by Maneage, which includes LaTeX and everything. So this project.tex is the file that I showed with all the numbers. Before we go into building the paper, everything is verified in this verify.mk. Everything is reserved with a checksum the moment we publish a result. And then, so the things that come into verify, so for example, I was showing a plot. You see the input data for the plot. They're from this, they're a plain text table. This plain text table comes from here. This comes from here. And this input.conf has the URL and checksum of the input. So you see, we have the full lineage of how the URL of the input turned into paper.tex. And with all the full analysis, and this can easily be expandable with Make, you know, and because something like the Linux kernel, GCC is built with Make. I mean, that's larger than any scientific project. It's easily expandable. And finally, because everything is in plain text, you can manage it with Git. So for example, you see we have all of the answers to these as a Git project. So if today and tomorrow you update your project, and this is how Maneage is defined. Maneage is actually a Git branch. So you branch off your project here. So you want to start your project today. You branch off from Git, from the main branch. You start to do commits in your project behind the scenes. The infrastructure in Maneage that contains like the low-level software instructions and things gets updated from user inputs. And then you can always merge your system. And then when you make your data release, you can, in fact, verify it. You can include the hash in your paper, like these two papers here. Look, we finished the abstract with the hash of the Maneage commit that we done this paper with. So then you can publish these everywhere. So for example, this is the Maneage papers archive repository. So you can just come here, go to other formats. Because it's just plain text, it's only 100 kilobytes. It's less than one figure in your paper or data release report. And then you can just come to download source. Look, I'm showing it here. And then you can just look. We have everything effectively here. Look, the full software in archive. We have how the instructions of how GCC was built for this project, how AstroPy was built for this project, including, of course, the LaTeX and the high-level analysis also. It's all here. And besides archive, you can also put it on Zenodo or Software Heritage. Software Heritage is a huge project which is collaborating with UNESCO for archiving human software heritage. And you can actually have all of this thing in one package to answer. So as a final slide, you can see that I'm just showing the future prospects. You see that it's great for researchers in other fields or PhD students to exactly see how you've done something, to verify, to test incrementally, to do machine learning. So like, for example, if you have hundreds of pipelines like this that are on Galaxy Evolution, you can use machine learning to find the best data set, the best analysis method, the best software versions to make a certain research project. And finally, so we got a grant from RDA 2 years ago, and it was also highlighted in Nature Astronomy with a really nice name, no expiration date. Please read this paper. It's like a public referee report. We had no idea that they wrote this, and then suddenly when this came out, and it was interesting. Okay, thank you. I'll leave you with these slides.
I do not see, thank you very much for that presentation, of course. I do not see any questions on this talk, but there are 2 comments so far. And the first one is from Dirk Petri, who says, interestingly, the way the ALMA Observatory is delivering its data products implements in a way what you are suggesting. We deliver the original raw data with a recipe to turn it into calibrated data and images. This was originally done to save archive space, but it also gives the user total reproducibility. And the second comment, very sweet and short from Specicia, is, this is incredible. And then Michel goes on to say that all we need is a machine learning step to write our papers completely automatically.
Exactly, because you can even blend in natural language processing into this. Because it's all in LaTeX macros, all the numbers directly link to the analysis command. Just imagine your English grammar gets mixed with the Python command that you used. It's exactly. That is really something I'd like to work with someone on natural language processing and machine learning to automatically construct sentences from a Python command, for example, or a shell command or something. Exactly.
I see no further questions on this talk. Are there any questions in the room? Doesn't seem to be the case, so thank you very much again for your presentation.
Thank you very much for organizing. Bye-bye.